Welcome to Fundamentals of Electrocardiography. My name is Harry Mond and I'm a cardiologist in Melbourne, Australia at the Royal Melbourne Hospital, and I'm also Medical Director of Cardioscan, the sponsor of today's webinar under the endorsement of the Asian Pacific Heart Rhythm Society. Today's topic will be the technological evolution of cardiac pacing. As you can guess, this is not an ECG topic, so why present it? Cardiologists, electrophysiologists, pacemaker implanters, pacemaker company personnel and cardiac physiologists have very little knowledge of the technical evolution and indeed the revolution that followed the first pacemaker implantation in 1958. Early transvenous implanters struggled with primitive and profoundly unreliable equipment, as well as having to design their own surgical methods. This is their story, of which I contributed. If you have any questions about this topic, then please enter them into the chat box during the presentation, and I will aim to address them at the end of the webinar. This presentation can also be accessed on the Cardioscan website under the Education section and available for watching at your leisure. Let us now enter a time machine and go back to those early days of cardiac pacing. This presentation will be memories of a bygone era which I participated in. Before we can do this, however, we go back to the 1930s, where the concept of cardiac stimulation was well recognised. Hyman in New York City in 1932 built a pacemaker, but there is no evidence that he ever used it. He, however, did state in his manuscripts that a person in Sydney, Australia, Lidwell, in 1929 also built a machine and used it successfully to resuscitate a neonate. Why was it then that people did not take up this concept of cardiac stimulation? The answer was simple. At the time, medicine was allowed to practice throughout the body, but not in the heart and brain. These areas belonged to an upper force that we did not understand, but was called divine providence. As a result of this, people were not allowed to tamper with the heart, and indeed, some journalists suggested that Hyman in New York should be hung up on a light pole for even considering this. Then, how then did we change? We go to World War II, and a young surgeon from Harvard, Dwight Harkin, was working in the field hospitals in the United Kingdom, and soldiers were coming in with areas of shrapnel in their heart, and he was not allowed to remove them. He had to then sew up the patient when it was noted, and the patient would be sent to die. Harkin then appealed to his superior officers, that then appealed to the United Kingdom generals in charge of medicine, and these in turn allowed him to remove a small number of these missiles and then present to them the results. After 25 of these, Harkin then presented his data with no deaths. He went on for the rest of the war to remove 134 shrapnel from the heart and again had no deaths from this. It was therefore recognised that man could operate on the heart, and from then onwards, from post-World War II, we developed open heart surgery. The initial surgery was for was for atrial septal and ventricular septal defects, which were closed using open surgical techniques, but not bypass surgery. The surgeons had no knowledge of the conducting system around a ventricular septal defect, and therefore many of these young children went on to have complete heart block post-operatively, despite an otherwise successful surgery. These included Dwight Harkin as surgeons. As a result of this, pacing interest was once again reignited. And in places like Minneapolis, epicardial leads and temporary pacing boxes were created. One of these pioneers was Earl Bygone, who, working in his garage, provided such equipment for the hospital, and he then later on went on to found Medtronics. So now we have the ability to operate on the heart, but we still have not got pacemakers. We require two major scientific breakthroughs to allow the development of an implantable pacemaker. The first was a transistor in 1947 in the Bell Laboratories in New Jersey, and here we have Shockley, Bardeen and Brattain, who went on to receive the Nobel Prize for this discovery in the 1950s. Here is a mock-up of the original one they produced, and you can see it's quite large. And from that went on to miniaturization, and today we understand that there are thousands, hundreds of thousands of these transistors in each of the chips. The second major breakthrough was the Mallory hearing aid zinc-mercury battery. Here we have a picture of them, and they were large, thick batteries that people would carry in their pocket and use for their hearing aids. The quality control was very poor, and therefore it wasn't really suitable for pacemakers, and early workers worked with Mallory to produce a double wrap RM type 2, which was later used in pacemakers. It sustained the pacemaker industry for 15 years. It was mercuric oxide, zinc and sodium hydroxide, and this produced mercury, which later on caused issues that people then banned this battery from being manufactured. You cannot seal it because hydrogen was produced, and cell rupture occurred as a result of this with sodium hydroxide leakage, which destroyed the pacemakers. So early pacemakers would last maybe 18 months to 3 years. The first implants was in 1958 in Sweden, and there was a rechargeable battery which lasted probably only about half an hour, and the recipient, Arne Larsson, received a further pacemaker sometime later and was frequently seen at the early pacemaker meetings, always sitting in the front row of every lecture. The second one was the fully implantable model created by Wilson Greatbatch, again in New York State, and was built by Medtronic, and you can see the 10 batteries that were required to make this, and it was then covered in a rubber. The lifetime was very poor in these pacemakers. Some months later, In early 1961, Graeme Sloman at the Royal Melbourne Hospital in Australia implanted the first pacemaker, probably in the Southern Hemisphere, or maybe outside Europe and America. The pacemaker recipient had many operations because the leads continued to fail and died approximately 3 to 6 months later. Graeme Sloman became frustrated in the mid-1960s as there were very few implants performed because of the reluctance of the surgeons who found the equipment completely impossible to work with. He then took it upon himself to try a transvenous approach. So in approximately 1965, in the new cardiac catheterisation laboratory at the Royal Melbourne Hospital, he started to implant pacemakers, but only 2 or 3 per year, as it was very difficult in a person who was not trained in any surgical techniques. In 1970, I joined Graeme in the cardiac catheterisation laboratory at the Royal Melbourne Hospital as a young, wide-eyed cardiologist with very little training at that time. So now let us enter the cardiac catheterisation laboratory with me and implant a pacemaker in 1970. The lead was a pacemaker lead Lima Shenanda EM588. Here is a picture of such a lead. The electrode was approximately 25 to 50 millimetres squared, was shiny stainless steel, and it was felt that the larger the electrode, the more likely it was going to make contact with the endocardium and therefore pace the heart. This, however, resulted in a low impedance lead which drained the power source. The lead itself was approximately 150 centimetres, and you can see here the structure with a terylene core, a stainless steel ribbon, and polyethylene insulation. Polyethylene is the material that is used every day in shopping bags and is not a particularly good insulator. The lead had no stylet and was implanted using a Kunan catheter. And you can see here the same type of catheter that Kunan used to self-catheterise himself back earlier. So let us now enter a cardiac catheterisation laboratory in 1970 and implant a cardiac pacemaker. Firstly, we cut down on the cephalic vein. Sometimes we use the external jugular vein, or even the internal jugular vein was used on either the left or right sides. The lead is then loaded in the Kunan catheter, placed in the vein and then progressed to the apex of the right ventricle. One of the issues we found is that the Kunan catheter and lead got stuck to each other by clotting blood and therefore required frequent heparin infusions. Once the lead was at the apex of the right ventricle, and remember there was no active or passive fixation device, the Kunan catheter was removed and the lead tied into the vein. It was then passed across the anterior chest wall and an anterior abdominal wall to the right groin, where the lead was then exteriorized. The lead was passed through this area using a very large bore needle, which was a painful procedure for the patient, as the local anaesthetics of the time were not particularly good, and the surgeons refused to give a general anaesthetic to such sick patients. Once it was in the groin, a indifferent plate was implanted as well, and the two leads were then connected to an external pacemaker for at least a week to make sure that the lead did not dislodge. Then, after that time, the surgeons would then implant the pulse generator higher up in the anterior abdominal wall. The lead at the time were unipolar, and no changes occurred for a few years until we got the stylet, which made a vast difference to our implantation techniques. When you wanted a bipolar lead, however, you required two twin parallel cables and this lead was massive and not particularly functional, and very few leads were actually implanted. How do we then reduce the bipolar lead body diameter? We use the changes to the conductor or to the insulator. The conductor changes that occurred was the conventional coaxial bipolar lead you're all so familiar with today. There's a central cathode, insulated, and then the outer anode also separately insulated. The materials used, as we said earlier, was polyethylene. Then we introduced silicones and then polyurethanes, and today we also use hybrid materials. Here is a silicone rubber lead where there is lead creep. That is, rubbing against the silicone rubber causes the molecules to build up and therefore reduces the thickness, and eventually the conductor is exposed. Therefore, silicone rubber leads need to be thick. Today we have more high-performance silicones which are more reliable in this regard. Thin polyurethane leads were introduced in the early 1980s and completely revolutionised pacemaker leads. However, after a few years, it was regarded that the popular soft polyurethanes degrade after 2 to 3 years of implantation, and there were hundreds of thousands of leads required to be replaced because of this. There was a hard polyurethane lead, which was much more stable, but too stiff and caused perforations. So both polyurethanes were not suitable for the pacemaker industry as such. So we have silicone rubber. Most pacemaker leads, it's not strong enough, it needs to be thick, but today we have better quality. However, it does require a protective overlay to prevent the breakup of the lead, insulation, and we use polyurethanes, which are too stiff for full insulation, but useful for overlay. A further insulation material are the hybrids. These were produced initially by a company in Australia, in Melbourne, and what they do is they create the strength of the silicone and polyurethanes without its disadvantages. What happens is that 80% of a polyether is removed and replaced with silicone rubber, and today we know this material as Optin, produced by Abbott in their leads. What about lead fixation? Historically, there were no fixation. A wedge was then produced, and this resulted in marked improvements as these wedges were caught in between and underneath the trabeculae in the heart. We then went on to passive fixation, as you can see here, of all companies, and active fixation was available at this time, but rarely used because almost universally all these leads went on to have a high threshold exit block. Let us now look at the cathode. Initial ones were large polished platinum iridium, as can be seen here. These were then reduced in size, and as a result of this, we had a high polarization, which is a disadvantage with pacing. We needed, therefore, to reduce the cathode size, but also to have a respectable polarization. And this can be done by materials such as pyrolytic carbon, platinum iridium, or titanium. But what is particularly valuable is that we have now created porous leads with titanium overlay, and in this way created a very small gross surface area to the lead, but the pores result in a massive increase in the diameter or in the actual size of the cathode, and in this way it reduces polarization. Despite these marked advances, we still had an issue of problems with high threshold exit block. Here we have a standard lead threshold curve seen in the mid-80s in the days following implantation. The stimulation threshold rises in the first 3 to 4 days, reaches a peak which is often higher than 5 volts, and therefore the output of the pulse generator at that time. It then falls backwards over the next week or two, and then enters the chronic phase, which is a plateau where the threshold is much higher than that seen at the initial implantation. How do we overcome that? We use steroid. And here we see the original design by Medtronic, where there is a plug placed behind the cathode, and there is a channel from the surface of the cathode going back to the plug, which is impregnated with dexamethasone. Following implantation, fluid enters the channel, dissolves some of the steroid, which then goes onto the surface of a cathode and reduces the inflammation. The results were astonishing. Here we have a study that I performed back in those early days at the beginning of the steroid revolution, where 10 leads were produced with steroid and 10 leads were produced without steroid, and as a double-blind study. And following then the patients for 10 years, half the patients were still alive at that time, you can see there are two distinct groups. Those with steroid, which remained throughout the whole 10 years at a plateau, whereas those without steroids went up after 2 weeks, and you can see it remained like that for the life of the lead. It's interesting that this wasn't taken up initially by physicians because of the fear of steroid causing endocarditis. And even conspiracy theories were rife in those days. There are 3 steroids used in pacemaker leads: dexamethasone sodium phosphate, dexamethasone acetate, which have identical post-implant data. And there's beclomethasone, a far more powerful steroid, which is today used for leads that do not have a plug and cannot have one incorporated, and the lead can be dipped in this, and it is so powerful that it too lasts just like the dexamethasone sodium phosphate and acetate leads for a long time. So steroid has been incorporated into plugs, and to the right you can see into collars. this design being created by Telectronics in Australia. And you can see also that active fixation lead on the right also can have a plug or a collar, and the result is that we have outstanding threshold levels for both passive and active fixation leads in the right and atrium and in the right ventricle. Let us now look at the lead connector. Historically, we know there was no connector on the lead, and this was created at the time of implantation of the pulse generator, and it wasn't a particularly satisfactory lead. So as a result of this, we had a number of unique unipolar connectors, with each company creating their own design. This caused chaos because as a result of this, these connectors, at the time of pacemaker replacement, the pulse generators had gone on to a new design. And as a result of this, the connectors had to be cut off and another connector placed on it, on the lead. Therefore, there was an attempt at connector standardisation, and you can see the thicker Cordis 6mm and the Medtronic 5mm. Medtronic made the thinner one, and in order for them to implant their lead into a Cordis pulse generator, we had a design made with a hole in that allowed to be placed over the connector, increasing its diameter, whereas Cordis could not be used in Medtronic pulse generators. But what about bipolar? Here we can see the results of the early bipolar leads with connectors, which are larger today than most pulse generators. As a result of this, there were a number of unique high and medium profile bipolar connectors created, and this again caused chaos within the industry and thankfully did not last very long, because low profile, more universal design connectors were then created in the mid-1980s. The first was the Medtronic, as you can see above, without collars and a long pin. And then there was the VS1A and the VS1B used by the other companies, which have on them either a large or small connector cathode, and we can then went on to create the IS1 connector, which was the 1B with the small connector terminal cathode. Let us finish off now by talking about programming. This is a non-invasive, stable, reversible change in the operating parameter of an implantable pulse generator. The first pacemaker programming was invasive, and you can see here in a design in the mid-1960s of a Medtronic pacemaker with a tail, and the tail tip was placed up near the surface of the skin and had a protective covering over it. If then an issue emerged, this could then be cut down onto, the covering removed, and there were 3 wires present. And by combining different combinations of these wires, we could increase the output, we could disable the pulse generator, which may have been a runaway pulse generator, or we could connect it to an external pulse generator. A second type of invasive and more popular type of programming feature was the Keith needle. On the surface of these early model Medtronic pulse generators was a nipple, and the nipple could be felt under the skin. Then under sterile conditions, a Keith needle was inserted and engaged within the nipple and then turned, and the turning then changed the operating parameters of a potentiometer inside the pulse generator, which then changed usually the pulse width to give increased energy output or change the rate. Non-invasive programming, however, followed soon after. The initial type was magnetic. There was a continuous type of magnetic action upon the pulse generator, which closed a reed switch and caused a programming change. Here we have a reed switch, and you can see there are two wires which are separated from each other. Place the magnet over them and they come together, and then open another circuit, which then changes the operating parameter, and removal of the magnet then fixes that program. Here is a typical reed switch, which is encased in a glass capsule, and there's an inert gas. The other type was pulsed. Let's have a look at the continuous magnetic fields. Here is the popular coffee grinder that was available at the time. Here, what we did was place the coffee grinder, which was just a magnet, over the pulse generator, and then turning it meant that the closing of the reed switch and changes to that controlled the pulse width. Another type was a Starr-Edwards pacemaker with a very heavy magnet, which was placed over the pulse generator and caused changes in rate. That is, every 16 beats, there was a 7-beat fall in pulse in heart rate, starting at 100 and finishing at 60. When you reached the rate you wanted, you just removed the magnet. By 1973, however, we also had pulsed magnetic fields, which was a remarkable advance. The first was the cordis, and you can see that what happens is that the magnet is turned on and off in a specific way, which then has within the pulse generator an embedded reed switch which flutters, and that type of flutter tells it what the changes you want. And therefore, we could have multi-programmable, and the earliest ones had 3 functions. Here we can see a number of these pulse magnetic field programmers, Cordis, Telectronics and Siemens working in conjunction with each other, or Telectronics later on. And these really changed the whole field of programming. However, it was radio frequency that changed the whole way we look at programming, and it is the system that we use today. The antenna is in the pulse generator to receive transmitted information. There is a very complex coding system to prevent inadvertent reprogramming, and it also allows multi-programmability, and today, of course, telemetry. And we have these templates that are placed over the actual over the programmer so that we can use them for different models. Becoming more complicated, and you can see to the right they're carried in an attaché case, and this is the first one to have a printer as well, not for telemetry, but to actually print out the program that you had just put into that pulse generator. These programmers had cassettes. For every different model, there was a specific cassette that was placed in the side of the programmer. The only issue with this is that I would be called in always on a Saturday night to the emergency room. I'd come in with the programmer and I'd reprogram the patient, only to find that someone had that cassette in their pocket, and that meant a very long evening in the emergency room. because of these cassettes being lost, the programmer did not last that long. And here we have a number of different types that followed soon after it. Again, Medtronic, now into Medix and Pace Setter, and some of these had printers as well. But with telemetry came the models which we are now familiar with today, and today's ones have now become tomorrow's ones, and we are now currently using these modern pulse generators. I'd like to finish off now by thanking you all for attending this seminar, and I have placed my email address here so that if you would like to speak to me, I am prepared to give you slides if you require them. And if you require more information or require a copy of this talk, then visit Harry's Corner for educational content, which is at cardiascam.co/Harry's Corner. Thank you very much for attending.